Now model was asked the following question. Why is a multiphysics simulation important? Well, I wanted to talk about that using the example of an electric motor. We will look at two different simulations. First, a single physics simulation using NC Maxwell, where we make an assumption of the metal temperature, the magnet temperature, and determine the motor performance in terms of its torque. And then we'll look at a multiphysics simulation, where instead of making an assumption of the metal temperature, we'll actually look at how the coolant temperature affect the metal temperature, which in turn affect the motor performance, which in turn, because of heat losses, impacts the coolant temperature. And we'll again look at the torque and compare the two. And actually, if you compare the two, you see the very different results in terms of torque. Actually, when we assume a temperature of the material of 22 degrees, we have a torque of 180 Newton per meter, while we actually do the multiphysics simulation, the actual metal temperature is 54 degrees, where the torque drops to 154 Newton per meter. A clear difference and a clear indication why a multiphysics simulation is needed. Now, to do such a simulation, we actually coupled Maxwell 2D to a 3D fluent simulation inside of the workbench environment. You see two Maxwell 2D simulation because we actually going to go one step further and look at the behavior of two different magnet material. The geometry is the same for the two models. You see the first fluent simulation connected to the first Maxwell 2D and the second simulation connected to the second Maxwell 2D simulation. The mesh are identical for the two fluid solution, and we'll compare all the results directly inside one environment using CFD Post. Here you see the 3D representation of the motor we will study. We'll actually only simulate a sector of it. Now you can see the magnets. It's also liquid cooled, so here is the pipe which carry the liquid coolant, and the rest of the electric motor is actually made of air, so it's air cooled as well. Now here we do the initial simulation inside Maxwell. It's a 2D simulation, and we see the temperature of the magnet. Now here we're looking at an instantaneous results of the 2D unsteady Maxwell simulation, and we're actually looking at the thermal losses. Of course, the thermal losses from the material, from the structural material, will be a thermal source for the fluid simulation. Now, what we're actually interested in is not looking at the unsteady thermal losses, but what we'll do is we'll time average them and extract the steady thermal losses and use that in the fluid simulation. Now, why do we do that? Simply because the frequency of changes of the losses in the electromagnetic material is much higher than the one in the fluid. So the fluid will never see the oscillation of changes in losses that the material is seeing. Now we actually switch to the fluent computation, and you see that we just imported the time average thermal losses that we computed inside Maxwell. It was very easy to do. It's automated inside the fluent environment. We see that the maximum losses are in the area close to the intersection of the stator and the rotor, and we're actually ready to perform the fluid simulation. Now we'll actually go one step further and look at two different material, SM2 CO27 magnet and NDFEB magnet material, and we'll actually see if there's any difference in behavior when we use one material versus another, if there's any difference in performance of the electric motor. And it's actually very interesting when we start looking at the results, because we can look at the temperature of the magnet for the two material, and actually the temperature predicted by the multiphysics simulation only varies by a few degrees. Now that being said, what does that mean? Does that mean that the actual performance of the electric motors will be exactly the same for the two material? No, because the magnetic properties of the two material can be very different and have very different dependency upon temperature. In the same way, I can look at the temperature of the liquid coolant for the two cases, and as you can see, the temperature is pretty much identical. So will there be any difference in the performance of those motors? And what a surprise when we actually compare single to multi-physics simulation. Look at the single physics simulation. The best performance is actually predicted with the NdFeB material. Whereas when we do the multi-physics simulation, where we actually look at the real temperature of the magnet, we see that the SM2CO27 material is actually giving the best performance. Pretty impressive for a result, pretty impressive to see how multiphysics simulation are important.